Yeah. So my name is Michael Hollinger. I'm actually one of the team leaders for a product that's called Power AI Vision. I've worked at IBM in a bunch of different roles over the last 13 and a half years or so. I've actually worked out of Austin for most of that, but I've had a chance to work out of IBM Taiwan as well for a couple of year assignments. My background is in high-performance software and around optimization of software for hardware. So like we were talking about earlier, but I've done clock-controlled software for like motherboards and systems and things like that. I got into Linux development a little while ago and then got deeper into that and now actually help to run a team that's doing application development around AI offerings in the company. So today we're going to talk about a few different things. First, I want to talk about why we as a company are in this space and really give a little bit of context. Second, I want to explain this tool, this pipeline that we're going to talk about, and get questions from you, and we'll talk a little bit more with the whiteboard and kind of chat about it more as developers. And then three, kind of look at the capabilities of the application and how we actually leverage those as we go out to build something that someone could actually go use in production. But first, actually have a little warm-up thing because it's been kind of a long day. So I want to ask everybody, what's a bike look like?
Wheels.
Wheels, okay. Two, I heard two. Handlebars. Frame. Brakes. Seat, okay. Gears. Pedals. Chain. Yeah. Tires, yeah. So, I mean, we're talking about features in the device, right? And you can kind of think about what a bike as an archetypical bike might actually look like, right? But if we take a look at real life, it's a little bit different sometimes. And one of the things that we actually see is that everyone kind of starts with, and they describe that bicycle actually in the upper left corner. And actually, I've done this a bunch of times. If you were to go sit and try to draw a bicycle without looking at one, probably about a quarter of the time someone draws a bicycle that actually can't turn because they try to connect the frame the wrong way. But like a bicycle looks a certain way from a certain perspective, right? But you can see that from the front, that's still the same bike as far as we know, but you can't tell that there's two wheels. Bikes can also be upside down. Bikes can also be things like a piece of art that technically is a bicycle, but there's a bunch of other stuff kind of attached to it. And in fact, this was a bicycle, and technically it still is by parts, but it's not really rideable as a bicycle, right? You can also see this one that I actually kind of like. It's a tricycle, but from the side it looks like a bicycle, right? So is that technically a bicycle or not? Finally, you have the special cases like a bike that will cover a child as well that has three wheels but still is a bicycle, and the literal bicycle that is two wheels and a person that has gears, it has brakes, it has a seat, it has all the things we just mentioned, but it does not look like that one, right? So all these things kind of fit in the realm of what's a bicycle for us. And this is the kind of thing that you end up with when you start talking about real-world deployments of machine vision applications in the wild. You have these kind of interesting problems that show up where things come out of left field, and you have to kind of deal with that and build that into the application, build it into the pipeline, and build that into your ability to actually deploy that pipeline out. And we're going to talk about that. So over the last several years, we've made a lot of innovations in the industry, and we've actually seen that machine vision types of problems have greatly advanced in terms of what capabilities are out there in the state of the art. So about, say, 7 years ago, you got about 3/4 of the time right if you were to ask a system, what is this picture? So there's different challenges out there. You can kind of see that the error rate was about 25–26%. We now got to the point where a deep learning-based application can actually best a human being given a certain set of images. And you're seeing that because we figured out that there's certain techniques and certain challenges we've overcome for applying and building out these massive data sets and figuring out how to actually architect a network in such a way that you can actually solve these problems in a way that's actually scalable and you can actually put out in production. So we've seen this kind of shift in the industry over time. For us, I want to talk a little bit about something that kind of addresses this, because this is a little bit important in the context of IBM, because a lot of people hear about IBM and they hear about the IBM cloud offerings, the IBM Watson branding, and things like that. I actually work on a thing that's called Power AI, and this is actually all kind of underneath all that, right? We're not going to be something that's going to necessarily be an API endpoint out on the cloud somewhere. What we're actually talking about is a software stack that's tuned for hardware, and we tune it at all levels here. That's part of the genesis of my group, Cognitive Systems. This is actually what we, as a group, call our entire organization, and that's intentionally a little bit vague because we build the microprocessor, we build the processor, the backplane, we build the system, we design the systems, we build the firmware for it, and we build the OS patches that are necessary for it on Linux, all the driver stuff. That's built by teams that sit like back here, sit across the street, and sit across the world. But we operate at all levels of the stack. And Power AI is something that actually pushes that optimization up into the layers of the stack necessary to apply machine learning or deep learning based algorithms toward problems. And this is something that's important because these are the kind of foundational things that a lot of people talk about as like the super low level of their applications, but really there's much, much, much more beneath that. And what we're doing with this is we're actually building, for example, distributions of TensorFlow, PyTorch, Theano, Caffe, like all the different things that you'd want into what we're calling a Power AI distribution. So you get a binary, get a container, spin it up, don't have to worry about compiling stuff or sorting out the configuration stuff. It just kind of works. That's the value prop we bring to it from a developer's perspective. The cool thing is because it's optimized for hardware, it actually scales really well. So we have a lot of cool things that show that we're really fast at doing certain things. We built the computer for that. So if you've heard of something called NVLink, NVLink is, for example, how NVIDIA couples their GPUs together. We actually have NVLink to our processor, which other people don't have. So we have extremely high bandwidth to and from the GPUs, so we can do things much more efficiently, much faster using these systems. And we want to bring that out and make that easy to use. That's why Power AI exists. In the computer vision space, computer vision as a whole is actually a growing market. So we actually see that right now it's about a $2 billion, $2.5 billion market, but year-over-year growth is going to see that it's actually going to be something that will be $11 billion over like 2022. And that's because there's this kind of inflection point that's happened where we figured out again as an industry how to start applying this optimization, start applying this hardware to these interesting problems. We were talking about it actually before the meetup that I can actually take a video feed and, given the right stuff, start telling about interactions between a customer and an employee in a retail space. And I can start measuring things about that and start telling about how efficient is this individual, how efficient is this particular store, and doing things to help course correct or help to improve that experience for the customer. So going back to my kind of AI stack for a sec, we actually, again, play at all levels of this. And the part that I work on is when we call Power AI Vision. Power AI Vision is an application that's optimizing that machine vision pipeline, which we'll talk about in a second, leveraging all the levels of optimization underneath it to help build a really easy to use, but still highly efficient piece of software and software-hardware combination. So this is something that is part of a broader play that we have, but again, it's not just like a Watson thing or not just a Caffe thing. This is actually kind of optimizing everything from the source this or activate at the level of like Python all the way down to the microprocessor itself and the buses in and out of the microprocessor. So we play at all levels of this and we optimize all levels of this. So we're in this space, and this is where we're going to start talking about the machine vision stuff. Because if you consider machine vision problems generally as a broad set, there's kind of a common set of problems that you have to overcome. And there's different players involved in that as well. So if we talk about bringing out a machine vision application, it's not just getting a data scientist to go out and build a model. First, I have to get a data set. I have to somehow curate the data set. I have to make sure it's valid and make sure it's good. I then have to get someone to go and train a model for that. I have to verify that model, and I have to hope that I got it right, go back and check that I actually did get it right, and keep iterating until I get to the point of being satisfied in however I define that, right? At some point, I actually choose to deploy that model. And that deployment is probably going to be at a different person that actually knows how DevOps might work, and they actually know how QoS might work, or quality of service or service level agreements might work for other parts of a business or other clients that you might have. And finally, there's actually the actual end user who's trying to go and leverage whatever it is all these other people built. Each one of those people has a different set of capabilities and different set of needs, but they all have to work together and they all have to do similar things to go and solve the overall problem. Traditionally, when we talk about machine vision software, machine vision applications, we kind of focus on the developer and we focus on enabling and building a really great piece of software for that developer. But that's not the whole thing, and that's not going to solve the broader set of issues that come up here. So what we actually do is we focus in a little bit on that kind of data engineer. We focus on the subject matter experts, and we focus on that data scientist and look at what are their needs and what are the things that you have to do in this space to help build out and deploy out that model in a way that I can use it. So this is that pipeline we're going to start talking about for the next part of the meetup. So for us, when we look at this, we actually consider the machine vision pipeline as something that is kind of a standard set of tools. So for us, we actually built an application that's available through a web browser, which I'll show you all in a few minutes. But it's all point and click, and it's all something that's designed in a way that you can label your data, train your model, and deploy your model in such a way that you're really never required to write code unless you want to. And to be honest, you don't have to know about the internals of it, but you can if you want to dive in. So for us, we look at and consider a couple of different capabilities. So we'll talk about these, and I'd be happy to take questions about this as well. But we actually do the same basic workflow for classification of images and for object detection. So when I talk about classification versus object detection, do you all know the differences and kind of what the capability of one is versus the other? When I say classification, that's actually saying, given an image, given a JPEG, is this a picture of a puppy? Given a JPEG, is this a picture of a kitten? It's not find the kittens or find the puppies, but rather just what is this image? So classification, typically problems are going to be the classical hot dog or not hot dog from Silicon Valley, which I have built like a dozen different times, a dozen different ways. By the way, MS Coco, the MS Coco data set, has at least 2,000 labeled hot dogs in its data set. And it's just entertaining to have to explain that's why that's on my test system every now and then. But classification is really asking the question, what is this image? Like what is this a picture of? And it's not trying to do localization or not trying to explain what's in it, but just overall, what is the image? You typically see things like heat maps when you talk about this, because it's very easy to visualize the output of the network. The heat map actually that we show here is I think the lowest level activation layers of the network. So it's kind of the final bits that are saying, yeah, this is a house with a pool or a house without a pool, and showing like what pixels basically are causing us to think that's why that is. A different thing is object detection. And object detection is answering a different question, which is, show me where this is in the image. There's a totally different technique for this, and it's solving a different problem, which is really object localization within the images, right? So the examples here we actually show are kind of a safety thing. So like, show me where the vests are. Show me the helmets in the picture. That's actually, for us, a technique that we actually use called faster RCNN. So if you're familiar with that, we actually we follow that, and we have an implementation of that inside the tool. But we use object detection to try to solve problems where people want to go and localize something in a picture. So if I took a picture of, say, this water bottle, I could find all the water bottles in the room or in the image, that kind of thing. one of the things that's important for us is that by considering this as kind of a pipeline, right, as a workflow for users, we find that there's this kind of iteration that occurs. So if you've ever played with TensorFlow or played with really any of the frameworks, right, and you've done one of the machine vision kinds of exercises, you find that you're going to mess with a data set, train a model, look at how it did, fiddle with it, go back, mess with the data set, and you keep kind of ping-ponging back and forth until you get to the point of being happy with it. So recognizing this is kind of a common flow, we actually built in the idea of using the model to actually label the data and validate that labeling and things like that, which I'll show you all in a bit. But this is something where we want to be able to switch users from generating labeled data to being more of an auditor of the system and just kind of overseeing the labeled data. Because it's just faster. If I have to go through and draw 200 boxes, it's going to take a while. If I can just fix up a few boxes, that's going to be way better for me. So let's actually take a look at it, because I think we can actually have a little bit of fun and talk a little bit more. So I actually have a copy of this running on one of our boxes across the street. And what we're doing is we're looking at a system that's actually running on bare metal Kubernetes. It's running on top of a Kubernetes. Oh, I logged out. Man, I got logged out from the tab. That's fine. So this is actually a box that's running Kubernetes on my system across the street. It's running bare metal. It's not in any cloud anywhere, but it runs inside of a machine called IBM Cloud Private. So I can run Kubernetes on whatever hardware you give me, basically. I can scale out and kind of do whatever. This is where we get into the kind of interesting developer focus, the kind of nerd focus, which is what I like. So we built the entire application on top of Kubernetes, and it basically sits inside of a Helm chart. Everything is containerized. Everything is a pod. So when I talk about the services that enable us to do the things that I just told you about, they're all running as containers inside this pipeline. And we built that way on purpose because we want to be able to enable users to get value from the application as a whole overall application. A image analyst from an insurance company is not going to know what any of these words mean, but if you're developing and building an app out on top of it, we'll provide you like a container that you can go use to go do stuff in, or we'll expose a REST API to you, or things like that. So when I look at this inside my browser, I'm actually looking at a instance of the application running inside of Kubernetes. And for us, that workflow that I kind of explained to you, we kind of see it, again, in these broad terms of really building a data set, prepping your data, training your model, and then deploying your model. Those are kind of the broad tasks that we kind of see people trying to do. So for us, when I look at my data sets, I can see a bunch of different things. And we have different examples that we kind of go through here. But I'll show you the US Grand Prix. So if I go to YouTube and hit play real quick, this is actually a video from the US Grand Prix that Formula One put out after the race last year. It's their highlight video. It's 6 minutes. Someone put it together after the race to tell a story about, let's see, this one's Lewis Hamilton, Max Verstappen, and who's the Ferrari guy? Thank you, Sebastian Vettel. So it's those three kind of duking it out for first place. That's the narrative of this video. And so they put the video together kind of highlighting the race. It's about a 90-minute, 2-hour race, but they culled it down to 6 minutes. This video is actually a video that I pulled into the tool. So if I go into label objects on this, and I unzoom me so I can see more of the screen, I have the same video inside the program, and we can watch the same video here. Again, I talk about building out data sets, right? One of the things that's important for us in machine vision applications especially is that we work with both images and video. And we actually combine those together into the same data sets. So I could easily drag a JPEG onto this and plop it in and have a JPEG image aside from the video frames I can pull out. You can see here that I spent a good like 20 minutes on this one frame, which was a really big pain in the butt. But I've labeled every single car according to the starting grid. And what I did is I labeled them according to their teams. Because if you don't know Formula One, the cars are 10 teams, 2 cars each. Each car is nearly identical, save for the number, and a little tiny black or neon yellow thing at the top. That's pretty much it. So even with like super high def video, as a human being, I can't tell them apart. So I'm not going to try to have the machine tell it apart either. But I can go by team pretty easily. So I labeled all the teams, and I went through, and I drew little boxes on stuff. And the way that works for us is if I go in and I can, like, say, capture a frame, that's going to go out and do a capture of that. And if I go over to 1 minute and 13 seconds, and I get it exactly right, whichever one I picked, that one, I can go in and I can just simply say, which one do you think that is? Is that Mercedes?
Looks like a Mercedes.
Yeah, it's probably Mercedes. This is how we introduce bias into models, by the way, which I'm totally gonna get to in this talk, so that's kind of it, right? So that that's labeling inside the application. So as a user, I just drag and drop on top of it. Go for it.
So my question, I think I know the answer, but just to verify, you're saying you gave the computer or your program the go train yourself, and then it's a fresh image, identify this car. You're not taking the delta of all the images to this point and saying, based on physics, it's got to be this car, right?
Correct. Yeah, I'm going to get to that actually, but you're right. We actually don't have a concept of time in our building our data sets or labeling our data. Everything we have here that you see is treating each image as a discrete frame, and each discrete frame is a discrete image, so there's no sense of continuity from one to the other.
Thank you.
Great, and it's actually a really interesting problem that comes up because as humans, we actually kind of intuitively know, given a video, that this thing here, a quarter second later, even if it's over here, is roughly the same thing. So there's actually work that one of my colleagues is doing around the idea of trying to build a network that kind of has that understanding, but we're like working on it, and it's not here. But for this purpose, right, we actually consider a video basically as a container of JPEGs. Like it's just that's how we see it, and that's actually how we write the code, to be honest. But as we go and capture stuff, I can go in and label things, and you can kind of see that I went and drew boxes on these frames. So I sat for probably like 2 hours over the course of an afternoon, and just sat here kind of picking stuff and drawing on about 200 frames-ish out of a 12,000 frame video, just to give you a sense of kind of the percentage of the video that I labeled. I actually trained a model on that. So if I go in and I go into my data set again. If I choose to train the model, again, we kind of try to make this something that's accessible to people who don't have a data science background. But they can still kind of know what their goal is. This is progressing you down that pipeline now. So presuming I've gone and labeled my video and I've labeled my images, I now need to train a model in the application. So for us, I can kind of guide you down that path and say, okay, well, what do you want to do with your data set? Do you want to do classification? Do you want to do object detection? Those two things. You tell me that, and I'll give you some more options. So I combine these together because in our labeling of the data sets, if I go back to that, you'll notice that in my USGP Golden, this actually is uncategorized technically because it's a video and it's all the same stuff basically. But if I were to go into a example that's like a medical example, we've actually gone and we've done work to set up the application so that I can go and do both labeling of specific things on an image as well as categorization of the overall image like I told you earlier. So I can use the same tooling to configure the data set for both use cases. So I go into my, go for it.
Can you use like existing knowledge to kind of train whatever this like example that you just gave as like like how do you recognize a cancer? Cancer, based on the information that you know as an SME, should be able to kind of train it that way instead of manually kind of like entering information and training.
Right. So that's one of the things that we've actually talked about on our team, and one of our developers is standing right next to you, and he and I have talked about this idea of annotating. Sorry, Carl. But we've talked about how we build the annotation pipeline into the system as well. So, but you'll notice that in all of our stuff here, I don't talk about file names. I don't talk about the contents, or I don't talk about the camera, or when the image was taken, stuff like that. We actually can track that. We just don't expose it through the UI. But there's extra data that comes from medical. It's just different file formats and things like that. But yeah, we've actually got an idea for how to do that in such a way that you can actually annotate the images as they're arriving in the system, so you're not having to sit there and click on stuff and say, yeah, this is normal or not.
That would be too manual.
Right. So it's a thing that we're actually aware of, and this thing that programmatically I can do, but I can't expose through the front end of the application.
So is it applicable to the example that you gave in the music also? In the F formula?
Yeah, actually, a perfect example is actually, I was actually thinking about this as I was doing this. I've been out to Coda, I've been out to the track, and if you ever walked the track, it's got some pretty distinctive visuals from certain points. So there's a turn complex that's the turn 12 corners that look a certain way, right? They just it's always filmed from the same perspective, and they always look the same way. I know that's what that looks like, so I know that's what that is. But given the fact that if I were to get the raw camera feed from Formula One or from the track officiants, I could actually just tell it's camera number 7, and I can load that into the system and know camera number 7 is at turn 12, so therefore all my video from this is from turn 12, and that becomes one of my categories. I don't have that data because I pulled it off YouTube. But that's totally a thing that we're aware of and we're designing for, we just don't have in the product. That's the exact kind of use case that's an interesting combination of both the visual and non-visual data that we understand about the system. Another example actually is if I have cameras that are attached to moving vehicles. I have not just the camera data, but I have telemetry about where the vehicle is. I know the vehicle ID. I might even know the driver of the vehicle. I might know what city or what its path is, or where it's supposed to be, and stuff like that. And all those things can actually be extra data points you can use to help either build your data set or help with other parts of solving your problems.
And Mike, so in the example of the medical imaging,
Yep.
they're already pre-labeled good, bad, whatever it is, right? Cancer, not cancer. The tool does allow you to load up
Yes.
all the good images and in one step, label
Yep.
them all good and then all the bad ones and label
Yep.
them all bad. So you don't necessarily have to go through each individual image.
Right.
Like-
Yeah, actually, I can easily go in here and I can actually say, for example, if I go into these, and I don't know what I'm doing, right? But because I am not trained in this, but I can assign all these two categories, and I can say it is one of these several issues, and it becomes a thing that becomes a workflow optimization. Just how do you scale that? We have APIs for everything we talk about here. So everything that's in the application front end that's actually visible on the screen is actually a React Redux front end built running in the browser. So everything that you see, every API, is exposed from our back end. So everything you can do from the browser, you can do as a developer. So if you want to ingest data in the system, we have a thing for that. If you want to label data, we have a thing for that. If you want to kick off training, we have a thing for that. If you want to make inferences, we have a thing for that too. So the whole idea here is that we're not going to hide anything from you. We're not going to try to obfuscate it. We're not going to try to authenticate it. We want you to be able to use it easily as an end user. But if you want to go build something that's bespoke engineered, you can go do that. And people are doing that kind of thing. So for me, when I go to train a model, I can choose which way I want to go. And if I choose object detection, notice that some stuff kind of changed on the screen here, right? I can actually choose what type of model I want to train. This is where we start going into more of that data science view of the world. And this is where we start exposing a little bit about the internals of the system to the user. If you were to just click object detection and hit go, you'd never know what YOLO or faster RCNN are, and you shouldn't need to care. But if you happen to know what those two things are, we can tell you straight up, these are the two models we have to choose from. You may choose one or the other. You may tune some hyperparameters, and you can hit go and let it train. I'm actually going to do that just for the sake of showing you all what it looks like. But for us, what's happening now is I'm actually spinning up a Kubernetes deployment of a pod that's actually going to go and train my model for whatever I just set as the defaults, which is 4,000 iterations. Under the covers, I'll actually show you, if I do a get pods on it, you'll see this training pod that came up 16 seconds ago. And if I go look at it, it spins up. And if you've ever used faster RCNN in Cafe, if anyone's ever messed with that, this might look familiar to you. That's what this is. We actually build on top of a lot of open source inside of the product. There's some stuff that's a little bit different here. You'll notice there's some extra messages about like app messages and some smoothing and some extra statistics that we actually pull out. These are because we actually instrument the application so that we can expose it to the front end. So as a user, if you've played with these kinds of things from notebooks, or if you've done work for this in your own specific applications or your own specific jobs, or just for fun, you're probably familiar with this view of the world. But the better thing is actually just look at charts and see what's happening, right? So we're actually instrumenting the output of the system, exposing it through the front end, and kind of showing you what's happening as the training progresses. And again, the idea here is we want to make it such that a end user who's not necessarily trained in deep learning is able to understand, hey, it's doing the right thing, or it looks a little wonky, let's go find a data scientist and actually go look at what happened. So one of our testers actually was playing with this and was just doing like the normal stuff you do to test software, and he picked a bunch of odd values and managed to make one of our test data sets totally diverge. Like the loss just went up here and stood up here. And it's the kind of thing that I can look at that and know that's not the right behavior. But there's more subtle things that might happen where like it may never quite converge, or it might actually converge too quickly and end up being overfitting or stuff like that. And you can kind of start to see those things. In fact, we're actually going to enhance this for a new version to add way more stats, like adding confusion matrices or other things to the tool, so you can actually really see what's happening under the covers.
What
So,
hardware resources are represented by one pod?
That's a great question. So we actually have an interesting kind of love-hate thing with Kubernetes. If you've ever played with Kubernetes with GPUs, the GPU plugins in Kubernetes are the Wild West, and they seem to change from every dot version to every dot version. So right now, GPU allocations in Kubernetes are on a whole discrete GPU basis. So when I go to allocate something for a pod, I have to give it a minimum of 1 GPU. And I have to give it any amount of RAM and CPU that I want, right? But that whole GPU gets given to that pod. So we make a simplification here to say this training job is using the whole GPU. So this is a whole Tesla P100, I think. Or actually, let's see, this is P or V?
Scaling up beyond like multiple GPU becomes.
Yeah, but we can do that as well. We're actually talking about that for our roadmap of how we introduce that to the users. But yeah, you can start doing things where you start scaling GPUs. The interesting problem is actually not scaling out to multiple GPUs. It's actually the usage of GPU memory for a given job, right? So like right now.
Batch size problem.
Yep.
With this big fairly soon.
So take a look at, for example, the output here, right? So my training job is actually only consuming about 3.5 gig or so, right? So I'm leaving memory on the table. This is because, based on stuff, this is what works, and this is efficient for us, and it doesn't break anything across the different platforms. But if you were to write something custom, you're leaving room on the table here. What we're actually going to do is we're actually working on how do you try to compact these together so they sit on the same GPU in a way that I can start running multiple things together and actually start understanding that. The biggest thing is that that's where Kubernetes is going. Like that's totally, like that resource allocation problem is totally a solved problem in every other space except for these. So it's going to happen. So we're now kind of just waiting to see when like device plugins are going to catch up and stuff. But we're going to have to solve it at some point. So as this goes, it's going to keep training. It's going to do what it's going to do. The final result, I'm just going to, I'll let it go. We'll let it rock and roll. The final result ends up looking something like this. So if I look at this, this one I did, this is actually what we're going to talk about more in a few minutes, but this model trained over the course of about 40 minutes, give or take, on my system. So it took 8,000 iterations, about 40 minutes. It's using Caffe under the covers, which no one asked me, so it's Caffe. But this is actually running all on my system across the street. So that's a, what did we figure it out? This is a bunch of P100s. So I'm running P100s connected via NVLink to the main CPU. So I've got that kind of high bandwidth link to the GPUs. And if you haven't seen one of these, the pedestal that's out there, that kind of big obelisk looking thing, it's a touchscreen. You can tap on it and you can kind of get an interior view of all the machines. So you can see what the guts of this looks like. And it's got these, if you've not seen what an XXM2 GPU looks like, it's this funky dual socket thing. It's not a PCI card. So it's got these two pin connectors, and it's this giant heatsink and chip combo that kind of sits down. So we actually have up to 6 of these on the back plane on the system, and 2 CPU sockets next to them. So the machine that we're talking about is built kind of balanced for these deep learning kind of workloads. And that's why the software stack exists, because we want to try to make it easy to utilize it. So if I want to go off and try to see how this works, I can go in and I can take my model, I can deploy the model. So if I go and pick that, I've actually already deployed it, but when I hit deploy, that pops up inside my workflow. So I keep moving through my workflow. This model is, again, another Kubernetes pod. And this pod is running now a copy of Cafe, just like the other Cafe. But it's wrapped around, it's wrapped in a web service. The web service accepts certain posts and gets, and I can tell its status and stuff like that. But fundamentally, I can give it a stimulus and get a response back. So if I go to my system and I drop frame number 180 on it, I can see the result that comes out. These are all the inferences that come out. And we actually expose what that looks like. So if I go into developer mode and do it for my other frame, you all can see that as well. So if I look at our response, the JSON is not very pretty, but let's just do this. There we go, much better. That's even much better. So we get back a bunch of information about the image, and for a user, what I can tell here is the image that we actually processed. There's the MD5 of it in case we're checking stuff. But I get a confidence, I get some bounding boxes, and I get a label. So we start talking about this not at the level of Cafe and inferences, but at a post and JSON kind of response. So it starts becoming more friendly to not plain, but a developer like me that doesn't necessarily know about the guts of the systems. So that's what we expose out to the front end of our applications, which you kind of get as a developer who's doing inferences in the system as well. So those inferences end up being rendered into something that looks like this, where I can start seeing little boxes. But the interesting thing is I can actually take that, and I tinker with Python, right? So I'm not very good at it, but I tinker with Python, and I can use this to take all my frames from my video, explode it into 12,000 frames like I told you. So if I look at the USGP directory in my system, you will see all of these. And I learned that Mac OS and BSD have a thing where if you do rm star, it actually does a weird thing when there's more than, say, like 9,999 files. It actually won't do it. It says there's too many, like star expands, and there's an odd bug. So I learned about some odd behaviors in Mac OS this way. But what we're looking at is actually something we call a code pattern. We actually post these out, and you can see the notebook, and it'll be in the link when we get done with this. But this notebook is one of our example notebooks that we put out to show how to use the APIs and show how to use the tool. The example we use is counting from a traffic camera. So I took it to F1 and kind of ran with it a little bit. But the idea here is that you can understand how to pick up and use the APIs from start to finish, and you can see all the code, see all the examples, see all the stuff that you have to kind of do that's not necessarily important to your problem, but important to solving the overall use case. So, for example, my frame parsing exploding code is this frame parsing exploding code. When I get back a single inference, it looks kind of like that, just like I showed you. And when we look at the results here, I can go and ask the system on a per frame basis, tell me what you got. Like, tell me what came back. So I actually wrote this in a way that as a user, when I go and do my inferences, I save them out to some JSON file on my local disk. Because again, once I make the inference, I kind of get it and I need it and it's done. I don't want to have to go and rerun that. It's in a field programmable gate array, which we just announced with Xilinx like Tuesday. So you can go out and buy hardware and drop it in and do stuff with it. And maybe we'll skip past that stuff. But really overall, the application end-to-end fits into, again, this idea of building an end-to-end workflow. And again, the idea is, do you want to help move the user through that workflow and make it so that whether they're an image analyst or a subject matter expert in a given field like insurance or medical, that they can do what they need to do, and then go hand off to a data scientist who wants to build that high-end model, and then hand off to that DevOps engineer who wants to go deploy to production. And all those people need to be able to work in the same space, work with the same data, work with the same artifacts, but do different things with them. So that's kind of my story. I'll have questions. Sure.
So it looks like on some of the footage you have,
Yeah.
the network's already labeled the number of items for you. So
Yep.
in some cases, the driver, whichever
Yep.
driver is there. Are you able to leverage that data, the labeling that's been
Oh
done
yeah,
for you?
absolutely. So that's exactly what I was. So as an example, right? When I showed the teal boxes versus the blue boxes, blue was me, teal was the system.
Mm.
So I actually went and I labeled. The reason why there was that 240 some odd frames is I labeled about at first I think like every 10th frame in the video. So I got a certain number and trained a model, got a result. It was okay. It actually was able to label cars, but it got the team names wrong more often than it got them right. So I went and fixed those up and then ran it again, and it did way better. Again, save for the Sauber Toro Rosso thing. And then fixed up those two specific teams, ran it again, and then got to the point where I can show you the video. So you can see it got it wrong. Like I didn't correct the Mercedes rear view bias problem, which I thought was, I left it in because it was a cute story, but this is something that if you're not paying attention to managing your data sets and not paying attention to what you're really using as your source material, you can really introduce this into whatever the application is. So in the case of labeling a bunch of cars for an advertising demo, that's one thing, but for other use cases that may be a much more interesting or much more problematic result that may occur from it. But yeah, we can totally leverage that when we start building up the larger data sets.
What was the resolution of the video image you were using?
That was great question. I don't know if it's 720p or 1080. Pretty sure it's 1080. Let's take a look. I think this is, what are you? Yeah, it's 1080. One of the interesting things that we do, again, it's just how faster RCNN, which is what we're using internal for object detection, how it works. If you've not used that technique, it has this idea of a native resolution for the network. So we actually quantize the input image to, at worst, or at best, 1,000 pixels by 600 pixels. So if you show up with a 8 megapixel image, you're not going to get 8 meg. It's just not going to happen. There's trade-offs between performance and yeah.
So if there aren't any other questions, I have more of a neophyte question.
Sure.
When you talked about Tesla, are you talking about the cars or some kind of, I thought I read there was some kind of compute block or something when you talked about the Tesla?
Oh yeah, so that's a great question. So I mentioned the GPU types here. So in the system, we actually use NVIDIA Tesla model P100s. That's just the brand name that they attach to it.
Okay.
Yeah, no worries.
I have a question.
Mhm.
So when you extract the pictures from the videos, so in the demo you said like 10 seconds. So I'm just wondering, like, for different types of videos, do you always do 10 seconds, or what is your standards to like actually balance like how to extract?
It totally depends. I mean, for me, so for us, we actually have support for anywhere from 1 second to an arbitrary number. So it just depends on what the source material is. What I try to do is, if I'm doing a demo like this or trying to build something new just to see what happens, I'll try to go and get about 50 images, give or take. And you'll notice 50 images is not a very big data set. That is not a big data set if you've ever done anything with any quantity. That's because we can take that kind of pre-trained base model and use that as our starting point. So I can actually get a reasonable starting point from that, and then start using the auto-labeling stuff to try to build a larger and larger data set. So I'll try to do like 50-ish and see how we're doing. Like when I started this, I didn't know if I could tell all 10 teams apart or not. Like I said, just your guess as good as mine. And it turns out it worked, so I did more and more to do that.
When you talk about transfer learning, what kind of model are you starting off with, and are you varying the number of layers you are training as you go along?
So we actually we use the same 2 fixed model architectures. So for classification, it's GoogleNet, and so if you've read the papers, it's GOOGLEN. Anyway, it looks like this. That one, GoogleNet with capital L, capital N. But we use GoogleNet as the actual network architecture. We do vary the final layers for the number of categories. So like for image classification, we will adjust that just because if there's 7 outputs, 7 categories, that kind of stuff. But the base architecture of the thing is the same.
How many layers do you adjust the number of layers you play with?
No. So it's GoogleNet's what, like 15 layers, 14 layers? Sorry, 16. Sorry, my bad. 16 layers. But no, we don't mess with that. We actually, again, like one of the things that's interesting here is we try to pick a common denominator that gives you a useful result quickly. So we don't expose the architecture of the internals of the network. That's why we're talking about the TensorFlow support and stuff like that. Yeah.
So you said that you could load telemetry. How would that be done through the tool? Like what kind of telemetry?
Yeah, so one of the things that we do is everything's got a Restful Api, and today the way that we expose that API is we basically take a JPEG, and the JPEG's the JPEG. But one of the things we're entertaining here is adding support for arbitrary JSON that describes that. So I can actually, today in the schema for the system, I can describe attributes of the images, which are just arbitrary key value pairs. So if you give me something, I'll just store whatever it is. So if you have GPS data, or if you have vehicle data or whatever, if we turn that on in the API, you can start storing that and exposing it.
So it's just through the REST API, not through the
Correct.
the web interface of this.
Correct. The real honest reason for that is it's just we're trying to add features at a certain pace, and we're prioritizing other stuff ahead of that. Go for it.
Is there anything you see, I mean, I don't know exactly what use cases you are running into, but anything to gain by having the video processed with temporal awareness, meaning with a memory network or something like that?
Yeah, absolutely. It's actually one of the things we're working on right now. So if I talk about the way we do object reco in the system today, or classification today, it's discrete quantized frames, right? So frame 1, frame 2, frame 3, there's no concept of continuity. So if I pick this up and put it down here, and I get a frame in the middle, you can't tell me whether it's going up or coming down, right? So this idea we're talking about is trying to add this idea of time series data to the network. So I start talking about really this idea of action recognition or action detection based on video snippets. And that's actually something that we're working on, and IBM actually went and helped build out the moments in time data set, if y'all haven't heard of that. Let me show you what this looks like. It's really cool. This is something that we're going to bring into the tool at some point, but moments in time is a well-curated, let's see, what do we want to see? How about driving? So moments in time is going to be very small little snippets for a couple seconds of whatever these categories are, and that is technically possibly driving. Every single time I do this, I discover something new and interesting. But this is actually a a different problem from what we've been talking about so far, because the recognition of the action is actually something that must account for that entire sequence of events, right? So given that the classic example I just told you, right? So if I put this down versus picking this up, playing them backwards should give me two different results. So if I do this, I should get putting down object or whatever, or walking downstairs versus walking upstairs. So yeah, we do see there's a problem there. And one of the interesting things that comes out of trying to solve that problem is you can kind of treat the data the same as a classification data set. So for example, these are all 4 or 5 second snippets of video. They're all categorized as a thing. So my workflow that I told you about where I'm categorizing or labeling data, same exact problem, same exact use case, same exact workflow, but the underlying model, network model architecture is totally different. We want to try to keep that same workflow in there for the user, so they're not having to do anything new, but the same REST API would be visible, so I could still throw a stimulus at it, get a JSON response back. That's kind of our fundamental idea here. We want to try to keep that to a common denominator. So as you build an application on the pipeline, you can keep, as things change in capability, you can keep up with it, and you can actually go do something interesting when we add a new feature or the industry moves and adds something new. I actually really like, so this is actually my favorite paper that I want to share with you all, but this is something that someone put out last year, and this is 1 year in computer vision. And I like this because it lays out a really good treatment on many, 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 many topics. And it helps to kind of ground you and starts at a kind of a high level of, here's what we mean when we say classification, here's what we mean when we say localization or object detection or segmentation, things like that, right? So it starts from there, but then it starts quoting and giving you a reference material, reference paper, examples, and showing you exactly what's happening in the industry. So you can kind of see that object detection as a whole, we're talking about RCNN, or faster RCNN type architectures, are really getting challenged by things like YOLO. So again, we're adding support for YOLO, or we added support for YOLO into the system. If you've not heard of YOLO, YOLO stands for you only look once. So rather than scanning the image, yeah, I know. So rather than scanning the image a bunch of times and kind of zooming in a bounding box based on what I think and proposing a bounding box, YOLO looks at the whole image and then tells me what's there. And entertainingly, if you like YOLO as a name, the second version of YOLO was actually called YOLO 9000 because yeah, no, it's really entertaining code. Like, I did not know that YOLO, or that GitHub supported, yeah, like I didn't know that you can go look at, if I go back to, there it is. I didn't know you could do this in Git commits. Like, I really didn't know you could do that. But like every time I look at this, like, I'm just a little bit amused.
So are those just Unicode characters?
Yeah, they are, yeah. Like everybody respects it and it does it, so there you go. But the reason why I mention this paper is that this kind of shows you what's happening in the industry, and it shows you what's happening in research, and it goes through and shows you what YOLO is capable of. If I look at this video, YOLO is doing the same kind of tracking I was showing you earlier. YOLO is only tracking 80 categories of objects based on MS COCO, or 85 categories of objects. So it will do things like umbrella, tie, person. It has no concept of the McLaren or Mercedes F1 cars, right? So this is where you start talking about how do you take the base thing that I have and leverage that for my custom application. This is where that transfer learning thing comes into play, because this is where the generalized model has a sense of, because it's been trained on stuff, what stuff might be there. But specialization of that for the F1 example or for a retail example or other things is where you start getting more value out of the system. Because like I kind of don't care that there's an umbrella there. What I want to know is where is James Bond in this video, right? And it can't tell me that. again, this is really nice because this starts telling you about what's happening in the industry in terms of things like image segmentation, which is something what's the direction we're going as well. Segmentation, if you haven't heard of that, says that given an image, don't just give me a bounding box back. Tell me pixel per pixel what's there. So tell me where the road surface is, or tell me where the pedestrian is, right? And we actually have a use case that we actually do, and you might have seen it on one of my things, but we actually have a crosswalk example where we have city crosswalk cameras, or city cameras at the corners. And there's a question that comes up, which is, how safe is this intersection, right? How do you measure that? You can obviously get stats for accidents and issues and things like that, but what if I were to ask you, how often did something almost happen but never actually occur, right? How often was there a near miss between a pedestrian and a bike, or a bike and a car, where it worked out okay, but it was almost not okay? So we actually have a demo we put together and a real proof of concept that's looking at traffic camera video. And you can define a region of interest that says, here's the crosswalk, right? So here's where the crosswalk is physically. And if I ever have a pedestrian in the crosswalk and a car in the crosswalk, something bad is happening here. It should only be one or the other, right? Like traffic law says it's either you or me. If it's both, something weird is going on. So I can start filtering my data set and looking for that and trying to understand, why did that happen, and trying to help the city fix that.
So since it's kind of dead, is that really true? Because when I walk downtown, people come.
So let me tell you about scooters, man. It's a thing, right? So like, I say that the crosswalk, I say like I actually don't know the real law for that, but my intuition is that if there's an event where there's both, this is a thing, right? This is something that we should look at, and you can start answering questions that are more interesting questions like that. So you can kind of use this to get an idea of where the industry is going. And you can get a sense for what the capabilities of the models are. Have you guys ever seen this? Check this out. So we actually get this question kind of a lot, which is, given that we can track cars and whatever, can I track people? Can I watch people move around in space? And it turns out, yeah, I can now, based on this paper. But what they're doing is they're actually doing human pose estimation based on a single camera. No lasers, no stereoscopic video, no extra funkiness with infrared. It is a single, basically GoPro. And what they're doing is they're estimating where everybody is, right? And again, I show this because this is something that I would not have guessed as possible 2 years ago, let alone last year. And this is something I can run at 10 or 12 frames a second now on a consumer GPU. And the way that this works is, again, it's doing that object detection that we were talking about, right? So they actually define in the network a basic human being as, if I click away from this, they define a human being as basically having a nose, ears, shoulders, elbows, wrists, hip, knee, ankle. And that's what it takes to be a human according to this model. So they actually go and they try to find for the videos, they search for those things and they try to localize those points on a person. And given that I can localize what the left knee should look like, and I can localize what the right knee should look like, and I can figure out that human beings normally only bend a certain way, then I can do an inverse kinematic model to figure out what the actual pose is. So it's the combination of that machine vision capability, the computation of inverse kinematics, which is like, how do you make this, like if I show you that person, how does their leg bend to result in that shape, to actually go off and derive that kind of stuff. So these are the kinds of things that are changing and kind of happening in the industry. And again, what we're trying to do is we're trying to build that pipeline such that you can go and plug in stuff like this to it. So when we talk about doing inferences in the tool or doing things with our data sets, you want to be able to go and label your data. You want to be able to take the output and do something with it. and we want to try to make it as friendly to developers as possible. So like building something on top of what we have here, I'd like to be able to say that, yeah, you can get your object and that's great, but that's not really the end goal here. Finding where the car in my F1 example is not really, that's not going to solve my problem. It's really answering the advertising question or something like that. So I want you to be able to build code on top of that to go off and solve that. Other stuff? Cool.
Okay. So thanks, Mike. That was a very engaging and exciting presentation. We'll be posting all this presentation and the paper and all the other material. And also, I think Mike will be looking to follow up if you have any question.